This video is going to explore shifting transformations for mathematical functions. A shifting transformation is obtained by altering either the input value to a function, the argument to a function, or the output value of a function by adding or subtracting a constant. The result of a shifting transformation on a function is to move the function left, right, up, or down. So the graphical effect of a shifting transformation is simply a kind of a transport of the graph in one or more directions. To explore this idea, I first want to look at it in an abstract setting. So I want to give you a picture that's not attached to any particular formula. And then after we've looked at that situation, we'll look at some specific examples, and I'll show you how you can apply this idea to graph, at least obtain crude graphs of a wide variety of, say, quadratics without doing too much extra work. Okay, so let's suppose that we start out with a graph of a function. And we're not going to specify what that function is because we just want to look at how the shifts adjust it, and we don't want to get caught up in the details of what the formula is for the function or anything like that. So drawing a generic Cartesian coordinate system, and we're going to draw a graph of y is equal to f of x, and I'm just going to make something up. Okay? And what I want to do is I just want to locate some of the key points on this graph, some of the critical points on this graph, and using those, I'd like to explore what the shifting transformation will do to the picture, its effect on the graph. So let's say that this minimum is located at the origin 0, 0, and this maximum over here, this local maximum, is located at -1, +1. Okay? So there's two key points on the graph, and then I'd like to see kind of where they go when we hit this graph or hit this function with the shifting transformation. So first, I'd like to look at shifted inputs. So we're going to look at the graph of, let's say, y is equal to f of x plus 1. That's a shift of 1. We're adding 1 to the input argument of this function. And then after we look at that, we'll look at a graph of y is equal to f of x minus 1. That's a shift in the other direction. These are going to give rise to horizontal shifts. And the way that these affect the graph can actually be a little bit counterintuitive. So it's interesting to look at this one first. So what I want to do is I just want to figure out, based on the original picture, where these key points would appear for this adjusted shifted picture. So again, I'll draw a Cartesian coordinate system, and I'm reusing the x and y variables to again stand in for the horizontal and vertical axes. But now I want to draw a picture of the same function with an argument shifted by 1, altered by 1. And so what I want to do is I want to kind of match up what's going on in the original picture with what must happen in the new picture. So let's look at these key points on the graph. Okay? If we look at this minimum, on the original graph, it occurs at 0, 0. All right? And that means that we read the x component first, y component second. So the input to the function, which gives us this minimum, gives us this 0 as output, is given by an input of 0. So if we look at the shifted version, we can ask ourselves what x value is going to give us an input that ends up being 0 to the function f. Okay? So if we input a 0 in this, we see that the output value, the y value, is 0. Here, in order to put 0 into the function, to make 0 the actual input that the function receives, we would need to select x is equal to -1. Okay? So we're looking at what x value matches up the thing that's in the parentheses. So on the original function, it's at 0, 0. Here the x value is -1. That will feed the function an input of 0 and give us 0 as output. So this point, this 0, 0 point, must be located at -1, 0. Okay? So we've matched up one of the key points. Original function and the shifted version of the same function. Okay? Next, let's look at the other key point. We have -1, 1. That was a local maximum for the original picture. And there, it happens when the argument, the input to the function, ends up being -1. And if we look at the shifted argument, x plus 1, the value of x that's going to make that equal to -1 is going to be -2. Okay? So we would expect to see that other key point happening at -2, 1. All right? So once we've mapped out some of these key points, a shifted function just has to kind of fill in all the same details. It has to have the same features. We were plotting f in the original function. We're still plotting f. We've just altered the way that the inputs are getting to that function. Okay? So the rest of the graph we just fill in exactly the same way. Okay? So the effect of adding something as a shift to the input argument, what it's done is taken our graph and it's moved it to the left. Okay? So if we change the magnitude or the size of the shift, we can move it further left. So we've added 1 to the argument. We've moved the whole graph to the left, exactly 1 unit. If we added a bigger number here, we would move this function over that many units. Okay? Or we could even put in a fraction. If we didn't want to move it quite this far, we could add a half and only shift it to the left half of a unit. Okay? So that's the effect of adding something to the input argument. Next, let's look at subtracting something from the input argument. Draw our coordinate axes. And again, let's just match up where the key points are going to have to fall on this shifted graph. So on the original graph, we have the minimum at 0, 0. So we want to know what x value is going to make the argument to f, that input, equal to 0. In this case, the answer is 1. So this, kind of corresponding to the other shift that we had, is going to move things to the right. Okay? If we look at our second key point here at -1, 1, we want to know what value makes the function, or gives the argument -1 to the function, and here it would be x equals 0. So again, we match up those key points and then we just fill in the rest of the graph. Okay. Right. So you see that when you shift the input of a function and you graph it, you get either a horizontal shift left or a horizontal shift right, depending on the sign of the shifting transformation that you've decided to use. Okay, so this is the effect of an input shift on a function that you've graphed. Next, what I'd like to do is just show you what happens when you shift the output. The ideas are similar, but shifting output is much more intuitive. Here, we add 1, but we end up shifting left, so actually towards the negative x-axis. But when we subtract 1, we shift the graph right, which might be different than your intuition. Okay, so just remember this. When you add a shift, you go left. When you subtract a shift, you go right. Okay, so next, let's look at a shift of the outputs. So, draw on our coordinate axes, and let's draw a graph of y is equal to f of x plus 1. So here I've added something to the output of this function. So it's the whole original function, but we're just adding a constant, kind of tagging it on the end. And now if we look at our critical point, our kind of key point here, this minimum that's occurring at 0, 0, if I plug 0 into the function, right, that should find the minimum of this curve, then this constant is adding 1 to that value. So the y value gets bigger by 1 unit. Okay? And that's going to happen for all the values of the function. So what's going to happen with this shifting transformation is the whole function is just going to be bumped up vertically. Okay? So adding 1 to the output of a function is a vertical jump. The function goes upwards, or shifts upwards, by the number of units that you add to the function there. So this key point will be located at 0, 1 on the shifted graph, and this other key point is going to be located at -1, 2. We've gone up by 1 unit. Right? So these result in vertical shifts. Next, let's look at y is equal to f of x minus 2. If our intuition holds up, this should shift the function down. And since we subtracted 2, it should shift the function down by 2 units. So again, let's look at this key point. If I put 0 into the function, I get f of 0 is 0, and then subtract 2 from it. So that ends up much lower than we started. And that maximum is going to be down by 2 units as well. So that'll be at -1, -1, which I haven't drawn very well, but we'll go with it. Okay. So this is kind of the basic idea. By adding or subtracting to the input argument of a function, we can shift a graph vertically. By adding or subtracting from the input of a function, we can shift a graph horizontally. And by adding or subtracting on the end, kind of tagging a constant at the end of a known function, we can shift the graph vertically, up or down. Okay? So this is the basic idea behind shifting transformations and their effect on graphs. What I'd like to do now is I'd like to show you an example of how this can be used to actually generate a graph of a complicated function. Not amazingly complicated, but complicated enough so that we might not know what it looks like just from intuition. Okay? So we're going to look at quadratic, and I'm going to show you how to rewrite a quadratic in terms of a shift of a base quadratic. So we'll think about y is equal to x squared as being a base function. We can draw a picture of what that looks like, and then it turns out that we can take a really large number of other quadratics and write them as shifted versions of that base quadratic. Okay? So let's look at y is equal to f of x. This is going to be our base picture, and we'll make f of x just x squared. If I draw a graph of this function, it looks like a parabola that opens upward, and its minimum, it's kind of one key point, is located at the origin. Okay? Now, let's suppose that we have a more complicated quadratic, but we're going to leave the x squared term with a coefficient of 1. That'll ensure that this works out with any other types of transformations needed. So let's suppose that we have some, call it g of x, and we'll define that g of x as x squared plus 6x, how about plus 4? Okay? So this is going to be our function, and what I want to do is I want to use the process of completing the square to rewrite this as a shifted version of the f that we started with. So I want to look at this as a shifted version of just x squared. So how does this work? First, I want to complete the square in the x's, and that's going to give me a structure like this: x squared plus 6 well, we don't want it to match up with that. Just a second. We need perfect square structure. So perfect square has this structure. X squared is the first term. We have a cross term, which has 2x, and I'll call it S for shift, plus an S squared. This is the shape that we're trying to make when we complete the square. And the reason that we want to make this shape is that all of this stuff together can be factored into x plus s quantity squared. And that we're going to think of as f of x plus s. There's the visualization. That's thinking about this g as being connected to the f that we started with, that original parabola. Okay? So I want to think of this, I want to make a perfect square pop out here. So I need to match it up with the perfect square pattern, which means I need to pick and determine what value of s is going to work in this process, in this situation. So we have x squared plus, my pattern for a perfect square has 2 times x times s. In my actual function g, I have this 6. So I want to think about that as 2 times x times whatever I need to choose for s to make it match up. So 2 times 3 is equal to 6. So I'm going to choose my s to be 3. I don't really have a free choice here. I'm stuck with the 6 x's that are there, but I need to link up the stuff that I have with the pattern that I'm looking for. So we have x squared plus 2 times x times 3. And to finish off this perfect square pattern, we need to have an s squared. So we need to have a 9 lying around. Since I don't see a 9, it's not in the original g, I'm going to need to kind of pull it out of thin air. And the only way that I can do that without changing the function is by adding and subtracting the same thing. The net effect of that is 0. It won't change anything, but it gives me the pieces that I need to complete the manipulation that I'm going for. So I'm going to add 9, that's the s squared that I want, and I'm also going to subtract 9. By putting those right next to one another, I know that I'm not going to change anything. I still have the 4 from the original function, so I'll keep that around. Okay? So this is the idea of completing this square. It's looking at what you have, finding the right value of s, and adding or manipulating the expression to give you the pieces that you need so that you have exactly this perfect square. All right? So now, once I've put all the pieces into play, I need to organize them according to the patterns that I was looking for. So these first 3 terms all together, they form this pattern of a perfect square, and I'm going to replace them with this factored version, this x plus s quantity squared. So for us, these 3 pieces give us x plus 3 quantity squared. Okay? And the remaining 2 terms are constants, so I can combine like terms there, and I'll be left with a minus 5, negative 9 plus 4. That gives me a minus 5. Okay? So now, I have these 2 pieces, and I can think about this or visualize this as f of x plus 3 minus 5. So I've taken the g that I started with, which had 2 instances of x. It really looks like a different function, but I've kind of organized it in a way to make it look like a shifted version of the original function that we started with. And this allows me to use these shifting ideas to draw at least a quick sketch of what this graph looks like. Okay? So let's see what we've got. We've got a shift of plus 3 to the argument, the input argument. That should shift us left 3 units. And then we also have a vertical shift. We should be going down by 5 units. Okay? So by combining those 2 shifts together, we can draw a graph of what this g of x looks like just by using the picture that we have from f of x. So let's try and get at least a reasonable picture of what this graph looks like. So Here's my coordinate axes. There's x, there's y. I know that I get my picture, my graph of G is going to have its key point moved over left 3 units and down 5 units. So if I take my original key point here, the original minimum on this quadratic, and I move it over 3 units and down 5 units, then the center, or the min of this parabola, should be located about there. Okay. And then I just draw the rest of the graph in. It's just a move, a transport of this original function to this new location. And I'll cross over somewhere there, somewhere down here. And we can go and try to do it more precisely than that, but that's essentially the idea. You can take a wide variety of different functions and you can think about them as shifts of simpler functions. Okay? So that's the basic idea behind shifting transformations, what shifting transformations do, and then an example of how to use this idea to graph quadratics that might not behave nicely, might not factor nicely, but still can be thought of as connected to kind of a basic picture that we can build on. Okay?